Were you there in the class where we did latent diffusion vaporization?
Yes.
That's right. So yeah, we mostly did a question about.
Basically, like need of fusion.
So did you do this?
Yes.
Yeah. Then we just did this question last class, and then questions, nothing else. So there was another question that I did, this one, and today we're gonna do this one. This. Okay. Right. So if you have answers to share, you can share, or else I'll start solving. So it says a jeweler wishes to harden a sample of pure gold by mixing it with some silver so that the mixture is 5% silver by weight. The jeweler melts some pure gold and then adds the correct weight of silver. The initial temperature of silver is 27 degrees Celsius. Use the data to calculate the final temperature of pure gold so that the final mixture is at the melting point of gold. So what does it mean? So you have a container that contains gold inside it, and this gold is made liquid. So they heat it up so much that it's now fully liquid. And what you do is you drop silver into it. And as you drop silver into it, what will happen is that the silver will melt. And they do this. So when you have normal pure gold, right, it's actually very soft, and then it bends very easily. So to make gold more solid or more stiff, what they do is they add silver, and that's how the carats work. Not carats. So yeah, carats silver cuts. So you have 22, 18, 16, right? These are actually how much silver proportions are there. So 24 is like almost pure. Yeah. So ওরকম করে কমতে থাকে। So silver proportion দেওয়া হয়, but silver দিলে সুবিধাটা কি? Silver দিলে হচ্ছে জিনিসটা solid হয়, so you can mold it into shapes more easily. Okay, so gold bars, for example, they'll be 24, but jewelry usually it's like 22, 18. Okay, 16 is less gold, more silver. So this is the process they do. Okay, so এখানে ওইটাই করতেছে, what they did was they took 95% gold here, so that means it is pretty much gold, and they added how much silver here? 5%. Now the gold initially was at some temperature, we do not know, and the gold will start to cool down, and the silver was initially at what temperature? 27 degrees Celsius, and will start to heat up. Eventually what will happen is that if you allow this process to go on for long enough and you have the right amount of silver available, the silver will start to melt in the container, and then what will happen is it'll merge with the gold. But the gold will also start to do what in the process? Cool down. And they said the gold will cool down and reach what point of gold? Melting point of gold. So final temperature would be how much? Melting point of gold is 1340. And silver, that's at minus 27 degrees Celsius, will heat up and also reach what temperature? 1340, because it's a mixture, right? The mixture should have the same temperature. So that's something you have to watch out for. This is degree Celsius, this is Kelvin. Okay, so yeah, that's something you have to look into. So yeah, that's how that's what the question is. So can you try? What should it be? 5 marks. This is the ultimate question from this chapter. I think you can tackle any thermophysics questions out there. Today we'll be starting a new topic called ideal gases. Okay, so it's a topic where I can start that. Right. So the monetary value changes because of the proportion of silver you have. So the equations are E equals to MC del T and E equals to ML. There's nothing else. For $1,439.7. Acha, I need to start ideal gases. So let me explain what this is. So you have this setup here, and I told you that whenever you want to do these questions, right, the best way is to approach with a graph. So you have the graph provided here for gold and silver. So for gold, I'll use this color here. So gold is at a starting temperature we do not know. So we'll consider that to be T. And the gold is going to cool down, and it'll reach the what temperature? It'll reach the melting point, right? So melting point temperature is 1340 Kelvin, okay? So the color to change. Right, so it's 1340 Kelvin, right? So this is what gold will do. So when you heat gold, right, gold or cool down gold, gold will go from that temperature to there, and you can consider this process to be energy taken in. Okay, so this is energy in. Now, what? Energy in this is this is energy out because this is cooling down, right? Energy out. Now, on the other hand, what you have here is you have silver. Silver is at what temperature to begin with? 27 degrees Celsius, right? How much Kelvin is that? 300, right? So it starts at 300, let's say, and it'll go all the way to that point. But the thing is, it can't go in a straight line to that point. The reason behind that is, in between, there is a temperature where silver ki korbe, melt korbe. If you look at the melting point of silver, is 1240, right? So it'll go from 300 to 1240, then it will melt, and then it will go to that point. So all this energy that you see here, that energy that's on that part, these are all the energies that are needed to melt and heat silver, right? So that's energy taken in. So this is energy in. Right, so all you need to do is now equate them. So how do you form an equation here? So you say that energy taken in is equal to energy given out. Who takes in energy here? Silver. So silver হচ্ছে আমরা একটু ট্রানজিশনটা দেখি, it's 1240, right? And final temperature is there. So for the first part of your increase here, which formula is possible? Yeah, MC del T. So we need to set mass here. It says 5% by weight of silver, and rest is gold, right? So can I consider silver to be 5 m and gold to be 95 m? We don't know the mass, but we know percentage, right? So just let's take 5 m. What's the specific capacity of silver in solid or liquid? It's 235. 235 into what's the change in temperature from 300 to 1240? So that's going to be 1240 minus 300. This is the amount of energy gained for the first part. Plus, what else is going to happen right now? Next stage is going to melt, right? Latent heat of fusion. So that's going to be 5m into what is the latent heat of fusion for silver? 105 kilojoules, okay? So 105 into 10 to the power 3. Plus, what is it going to do for the next part again? Heat up. A part heats up. So what's the formula going to be? MC del T. And the change in temperature here is 1240 minus 1340. Or 1340 minus 1240, sorry. Right. Equals to, what is the energy given out here? So the energy given out is entirely by what? Gold, right? So what should that be? So the energy given out is going to be M, 95M, into specific capacity of gold is 129, into what's the change in temperature here? T minus 1340, correct? So once you solve this equation for T, you should have the answer. Okay, that should be it. So to kore dekho ki ashe. That's not possible, right? Oh, that was the change. 99 point. So 1340 plus 99.76 is how much? আচ্ছা এমনি করে দেখো সবাই, এখানে m ক্যান্সেল আউট হয়ে যাবে. Yeah, because the answer is a little different. One 140 148. আচ্ছা হ্যাঁ হ্যাঁ 1482.6. Yeah, correct. So 1483. Is that okay? Any questions along about the borough? So yeah, one more time, let me clarify what's going on here. On the left-hand side, you have all of these things where your silver is gaining heat. And on the right-hand side, you have these where silver or gold is losing heat. They both come to a common temperature. That temperature is T, not both come to a common temperature, both come to 1340. And gold comes from T to 1340. So you have to find that T. So all the energy in must be equal to all the energy out. So that's how we get our answer. Okay. Suggest a suitable thermometer that could be used for the initial temperature of gold. What kind of thermometer can we use? Yes, okay, so thermocouple. Clear. Okay, so we are done with thermal physics. I'll just quickly go to the checklist. and see if we have covered everything. So Ashiji chapter to start with is quite small, but there are a couple of very big derivations out there. So yeah, this is done. This is done. That is it. That was it, and we are done with our thermal physics. This Sunday you'll have or Saturday you'll have a test on this. Okay, so just some similar types of questions that we have done. Right. So let's start the next topic. How did you understand that the gold started at a higher temperature than the melting and decreased to that point? It's because if silver is cooler, right? Shouldn't gold have to be warmer for them to come to a common ground? So here, right? So I know that the silver is cold and it warms up to that. So naturally, gold must have been warmer for it to cool down to that, because gold is going to lose energy and silver is going to gain energy. So naturally, it must have started at a higher temperature. Okay, so let's see this new chapter. Some basic stuff asked wrap up. So the first thing is you need to know what the mole is. So I'm pretty sure you know about this. You probably know about this better than I do, because chemistry it's fundamental. Understand that the amount of substance is an SI quantity and base unit is mole. Use molar quantities where 1 mole of any substance containing a number of particles of substance equal to the Avogadro constant, right? So definition is given here. Definition ta hocche jigesh kore na, but just generally bhalo. Amount of substance that 1 mole of substance contains. Amra key reference nei for this derivation or this definition, carbon 12. Do you know why we take carbon 12? No, that's silicon. Right. So the reason we take carbon is because if you take actual elements, right, like hydrogen, helium, we'll do this in our physics. What's the mass of hydrogen? So it's not 1. Okay. What's the mass of helium? It's 4 at the top. 4 and 2, right? It's not 4 actually. So you'll find that as we go through all the elements in the periodic table, right, the numbers that you were aware of, they're not true actually. They're rounded up. And one hint of this was there in your chlorine 30. Yeah, why was it 35.5? Because there are isotopes out there, and the fraction of the isotopes available in the atmosphere or naturally altered ratio was a common number to use, right? So it turns out for almost every element, the number that you see is actually a percentage of all the water out there, isotopes, right? So therefore, the actual value fluctuates, and the actual value is not 1 or 2 or 3 or 4. These are not discrete quantities. These are actual masses out there. So to find like a reference, right, we didn't have any good sample out there because all of them had a lot of isotopes out there until we came across what? Carbon. Carbonate cano is a very good example because carbonate mass, it is actually 12. 12.0000000, then some numbers show up. So it's very, very, uniform at a number. So that's why you use carbon as a reference. Okay. Other elements and numbers below fluctuate, right, because of the ratio in which you find their isotopes in nature. Okay. So carbon 12 is because of that. No. No, those are not stable enough to be found in nature. Artificially করা যায়, but nature হচ্ছে like chlorine, তারপর হচ্ছে carbon 14 যেমন একটা আছে ওটাও পাওয়া যায়, but mostly it's carbon 12. হ্যাঁ, base হিসেবে ধরা main reason হচ্ছে because of its decimal places, so it's very accurately calculated. Right, so that's what 1 mole is. Now তোমরা আমাকে একটু শিখাও, what's the symbol for mole? Small n, right? Very good. So small n is mole, and what's capital N? Yeah, number of particles. So does anyone know what do you get when you find this number of particles divided by n subscript a? N subscript a, by the way, happens to be, right, 6.023 into 10 to the power 23 of anything, right? It doesn't need to be atoms, it could be stars as well. So what do you get when you divide these two? Yeah, mole number. So mole number টা হচ্ছে a ratio of the actual particles divided by the Avogadro's constant. Okay, so this is what you need for physics. I'm just only going through the ones that we need for physics, which is very basic. Okay, so this is the first one equation where n that you see here is number of particles. You are more aware of another version of this equation. This is right. Constant. The one that you're aware of is about mass. Yeah. So what n by m1? Yeah. Right. So the other formula is n equals to the mass divided by what? Molar mass, RMM, relative molecular mass, right? So molar mass. This is not that common in physics. We have them though. We have this in our radioactivity chapter, okay, where you need to find a number of particles in something. So yeah, this is more or less everything that we need to know for physics. Physics একটু জানলেই চলবে. And this is the constant. So I'll give you a question. See if you can answer them. Right, look at this. Some examples, some basic prerequisite before I can start the chapter. So it says that you have a sample of hydrogen gas that weighs 200 grams. Hydrogen atom has a relative mass of 1 gram. Find the total number of hydrogen gas molecules in the sample. So how many hydrogen gas molecules are there in the sample? That's the first one. The average velocity of hydrogen molecule is 550 meter per second. Find the internal energy of this sample. What assumption have you made? Or it too complicated, but first it's দেখো পারো নাকি? No. কত? 2 point what did you do? Why? হ্যাঁ, exactly. আমি তো হাইড্রোজেন অ্যাটম বলি না, হাইড্রোজেন গ্যাস তো হচ্ছে molecule which is H2, right? It's not just an H there. আচ্ছা আমি করে দিচ্ছি. Some of you look very confused. All right, let's look at this one. First one. A sample of hydrogen gas weighs 200 grams. The hydrogen atom has a relative mass of 1. Find the total number of hydrogen gas molecules in the sample. So one atom has a relative molecular mass of how much? 1 gram. Does anyone know what is a relative molecular mass or relative mass? A 1 gram মানে কি? Ratio. Not seeing anyone else got it or not. No, that's not convincing. Let's say I don't have chemistry or physics. Tell me what this 1 gram means. Are you telling me that a hydrogen atom is 1 gram? No, that's just absurd, right? That's like a grain of rice, maybe. So what's 1 gram here? Average. Okay. Anyone else? So let me clarify. So turns out the mass of hydrogen is not 1 gram of an atom, right? The actual mass of we have this in A2 plenty, so I can start, right? And I think you know this. One proton is actually 1.67 into 10 to the power minus 27 kilogram. That's the mass of one single proton. Okay. Now, when you have hydrogen, hydrogen is very unique because it is actually just what? A proton. Hydrogen is just a proton. If it has an electron, then it becomes the hydrogen atom, but it's essentially just a proton. It doesn't have a neutron in it. Okay, so this is your hydrogen here. So the mass of a hydrogen atom should be what basically? One proton and what? One electron. Wouldn't that be the total mass of a hydrogen atom? The mass of proton is 1.67 into 10 to the power minus 27 kilogram. That's actually the mass. So if you had one hydrogen atom with you, that would be the mass. And the mass of an electron is 9.11 into 10 to the power minus 31 kilogram. Now, compared to this value, this is very negligible. So I'll give you a reference. It is really 1,000 why? This is like less than 1. So isn't that very negligible? So eventually the mass of a hydrogen atom is essentially the number of what it has, proton, which is 1.67 into 10 to the power minus 27. And this is it. This should have been it. Unfortunately, this number is too big and too tedious for calculations and comparison. So Takunraki they decided that they will replace this number, right, with a new number. What do they call that? 1. And ওইটাকে বলা হয় 1 AMU. Do you know what AMU stands for? Atomic mass unit. Okay, and ওইখান থেকে আমরা হচ্ছে ট্রান্সলেট করে এটাকে গ্রাম হিসেবে ধরে হচ্ছে হলো কেমিস্ট্রিতে ইউজ করি। So কেমিস্ট্রিতে when you do like a Ca+2 calcium agent, right? Do you know what the or tell me an element যেটা সবকিছু তোমরা জানো, which element other than hydrogen? Carbon. আচ্ছা, কার্বনের mass number কত? 12. Proton number কত? 6. And if it was an atom without electrons, what would its charge be? Plus? Plus 6. That's okay. So no, there are versions of this. So this is 12, this is 6, this is plus 6, right? Do you know that none of these are right? Into right. I'll tell you why. First of all, plus 6 is not the charge of a carbon atom. It is actually what? No, it is actually plus 6 into 1.61 into 10 to the power minus 19. Okay, or take a relative charge. So the point I'm trying to make is that in chemistry, you use some numbers, right? Ogla are only good enough for calculations of chemical reactions because you're working with the same ratio. When it comes to physics, right, you have to use what units there? SI unit. AMU is not an SI unit. Okay, you can't use that. Also, a plus 6 data at a standalone number. What's this unit? It's a unitless number, right? So what is this thing called? Yeah, it's called a relative charge. Okay, so relative charge of electron is what? -1. What's the relative charge of proton? +1, right? But আমাদের physics, whenever we do our math, we need to use what charges? The actual charges, right? Similarly, এটা 6 না, এটা actually কি হবে? 6 into 1.67 into 10 to the power minus 27. That's the actual atomic mass, right? আর এটা কেমনে বের করবে? এটা আরো complicated. And all of this we have later on in a chapter called radioactivity. This is going to be 6 protons and 6 what? Neutrons, right? Do you know that carbon has 6 protons, 6 neutrons, and protons and neutrons are mass same? Neutrons are slightly what than proton? Heavier, right? So what you see here are just what values? Relative values. Okay, when it comes to physics, you have to use their what values? Actual values. So a conversion to শিখতে হবে। Anyways, let's get back to what we're trying to solve here. So if I have hydrogen gas, how many atoms of hydrogen should I have? 2 of them, right? So that's the mass. So if I want to find mole number, because I want to find number of particles, right? What will I do here? Mole number is equal to what? The mass. How much is that? 200 divided by what's the molecular mass? 2. So how much is that? Yeah, 100. And therefore, how do I find the number of particles? So we know that mole number equals to n divided by what? Avogadro's constant. So what's my mole number? 100 into Na is what? 6.023 into 10 to the power 23 equals to n. So therefore, the number of hydrogen molecules in the sample is how much? 6.023 into 10 to the power 25 molecules. Physics say molecules, atoms, interchangeable na. Kono jagay actually হওয়ার কথা না interchangeable. Okay, but এখানে খুবই important. So how do you overcome this problem? Because I understand some of you might not have chemistry. So you wouldn't know what a molecule is or a atom is, right? So there's a way out, a very simple way out, the one they allow. You can just say 6.023 into 10 to the power 25 particles. Particles could be atoms, ions, it could be anything, right? So it doesn't really matter. So if you're confused, right, just say particles. Particles is like a better version, okay? They allow it. But then if it's already written in the question, gas molecules, right? Why just not just use molecules? I mean, you know that, right? Acha. So let's move on. Yeah, I mean, chemistry te ja koro otai koro. Acha, egla koro na. আমি এটা জাস্ট বললাম যে হচ্ছে ফিজিক্সে what we need to do is we need to work with actual values. কেন actual values? Because eventually এটার unit কি আসবে এখানে? Kilogram. And when you want to find kinetic energy of a particle, right? Are you going to use relative mass or their actual mass? Actual mass, right? Kinetic energy formula key, half mv square. And mass should be in what? Kilograms, right? So don't you need to take the kg value? So এটা দিয়ে কাজ করতে হবে. Okay, let's look at this one. This is a little advanced for you guys, but I want to start off with this. Average velocity of hydrogen molecule is 550 meters per second. Find the internal energy of this sample. So if I gave you a container, look at this very carefully, okay? You have a container and there are a lot of hydrogen gas molecules inside it. I want you to find the internal energy of the hydrogen in this container. Was it possible to do so for solids and liquids? Internal energy? No. Why was that so? What was the formula for internal energy that I taught you? The actual internal energy is equal to the sum of your random K plus what else? Potential energy, right? Now, if I give you a sample, let's say a table, why can't I find the internal energy of a table? Yeah, we don't know what ratio the K is. We don't know what ratio the P is, so we can't. Can we find the change? Yes, and that's what we just did earlier. The change when temperature changes is mc del T. The change when state changes is what? ml, right? So that we have seen before. But right now, for a solid, we can't find this. For a liquid, we can't find this. But for a gas, we can. And I gave you an assumption that allowed us to find it for the gas. Does anyone recall something very unique about gases? Yes? That's in the spin. Right, exactly. I told you that whenever you have a gas sample, right, the gas particles within the sample do not have what energy between them? Potential energy. And yes, when it comes to K, they only have one type of K. What is that? Translational. And the formula for translational K is actually part of your syllabus since grade 6 or 7. That's your typical K, right? So what's the formula for translational K? Half mv square. So if I now want to find the total energy of all the gas particles here, what would I find? I'll find the total what of them? K, right? How can you find the total K? So that total K, which by the way would be my what as well? Total internal energy. And why is that so? Because what assumption have you made here? We assume particles only have what? Particles only have translational K. And what don't they have at all? No potential energy. See, eventually the total kinetic energy that you have can be found using what? Half mv square. The question is, how much is my mass going to be? What was the sample mass I gave you? 200 grams, right? So 200 200 the korba na kemne korbo? Acha eta ekটু আমাকে বলো কিভাবে করব? I've given you most of the information. এখন see if you can figure this out. How do I find the K of one particle? Yeah, what was it? Yeah. Mass is this one. Yes, correct. We can't use the mass of the gas here. Why can't I use 200 here? Can anyone tell me? Remember the question said 200 grams? No. Why can't I use 200 here to find the total energy? Yeah, it's the whole gas. It's the whole gas moving around as a ball. No, right? What's moving around? Individual particles. So you need to find what here? The K of individual particle, right? So individual particle value can be half into what's the mass of a single hydrogen gas? Huh? No. Yes, correct. 2 into 1.67 into 10 to the power minus 27. This value that you see here, this is the mass of what? One single hydrogen atom. But I'm dealing with what here? Gas, right? So that's what you're doing into 2 into velocity kichilo 550 square. Can somebody check what the value is? 5.05. 5.05 into 10 to the power minus 22 joule. But is that the internal energy of the gas, or is that the internal energy of or K of a single particle? So how do I find the total? Yes, very good. That's exactly what you do. Okay, so that's the only reason I did this question, because some other molne a active question ashe that they'll ask you to find the total energy of the gas, and this is how you do it. So therefore, total energy is equal to energy of single atom, energy of single atom, or a molecule, single molecule into number of molecules. So that's 5.05 into 10 to the power minus 22 into number of particles কত ছিল 6.023 into 10 to the power 25. Can you check what the value is? 13,030. 30,427 joules. So yes, if I want to find the total K of the internal energy of the gas in this room right now, I'll find the amount of gas that we have and find the number of particles of gas that we have and multiply it with the K of one single particle. We made a couple of assumptions there. Number one assumption is what? That the gas in the room only has what energy? K, translational K, and it doesn't have what energy at all? Potential energy. This is very important, okay, for what chapter we're going to do right now. And secondly, we made an assumption is that the molecule has a velocity of how much? 550, right? It's what velocity? Average. Okay, it's the average out there. Of course, in a room, you have particles that fluctuate in energy. It's variable. Okay, so we took this as an average. Yeah, no, there's no chemical bonds. Okay, so when it comes to particles, right, the potential energy is the bond. So we are assuming that the gas particles are so far apart that the typical bonds that hold them together is almost non-existent. No, and do you know why? Yeah, so the gravitational constant is 6.67 into 10 to the power minus 11, right? So the value is so small, and with these masses being even smaller, you find that the forces are almost non-existent, like 10 to the power minus 40. So therefore, we can completely ignore them. Yes, based on the planet, not you individually. Your own gravitational field is very weak, very, very weak. So it's the planet that can apply something appreciable. Is there a planet with the gas has high what? Yeah. The mass is very high. Also, so is there a planet where the effects of gravity is appreciable on gas particles? Yes, Jupiter. So Jupiter's size is so big, it's fully gas, right? But there's a point within Jupiter where you'll start to experience like almost solid behavior near the core, but it's entirely gas, right? So why is it like that? It's mostly to do with pressure. So when you pressurize from outside, things turn into liquid, right? That's what's happening there. So it's not more gravity; it's more about you compressing the particles and bringing them close enough that they change their state. Right, so let's move on. We are done with the small part. So is there anything that you have confusion with? Let me know. So just taking it quickly for your chapter, symbol is MOL, small alphabet, and it's number of particles. Okay, it's a measure of number of particles. Can you give me an alternate to mole? Mole ছাড়া অন্য কোনো নাম কিছু use করা যায় for amount of substance? Yeah, dozens, right? 12. When you have 12 of something, what do you call it? A dozen, right? Mole can be the same. Mole is just how much of something you need to have. Yeah, that is what a mole is. Okay, so dozen is fine as well. So a mole is not a chemistry thing. It's not a particle thing. Yes, it was particles that made us understand it. But can I have a mole of stars in the universe? Yes, easily. I mean, that's not a big number, right? Can you have moles of grain of sand? Yes, right. So it doesn't need to be atoms or molecules. It could be anything. Okay. All right, let's start. So, start because next class I'll give more details about this. This is the ideal gas assumption. Okay, page 55 to Jao. Very interesting chapter. Okay, shall I screen it? Let me explain what this is. You have some idea about this topic from what I understand from chemistry. So, all levels. Okay, so let me explain what this is. So, listen carefully. And the chapter is very small, but it's very theory heavy. Okay, so this is the year 1700s. We have started investigating gases out there, and while investigating gases, right, we came up with certain laws. And one of the famous laws back then was called the Boyle's law. And Robert Boyle, right, physicist, came up with this idea that if you have a container with gas inside it, if you compress the container, right, and you decrease the volume, what increases there? Pressure. And he found the relationship to be inversely proportional, like proper inverse. So half the volume, double the pressure, right? It was called the Boyle's law. And that was it. P is proportional to what? 1 by V. Okay, that's the end of it. But he made an assumption there. He said what had to be constant? Temperature and number of substance, like the gas had to be fixed. Around that time, there was another person called Charles. He came up with Charles' law. And Charles' law stated what? That volume is directly proportional to what? Temperature, okay? And pressure is 1 by volume. And then there's another law, pressure with temperature. What is that called? It's just called the pressure law, right? So what happened was, these laws were moving around, like, people were using them, but they were all individual ideas of the same thing. It's just imagine, remember there was a formula F equals to ma? So let's say somebody figured out, oh, F is proportional to A. Somebody else figured out F is proportional to what? M. And there was another person who figured out mass is proportional to what? 1 by acceleration. Aren't they just the same equation all along, right? So and at that point, people decided to come up with an equation to converge and combine all of them. And eventually they came across an equation that you're aware of. It is, right, it is the ideal gas equation. PV equals to nRT. এখন আমরা এটা derive করব. That's what we're going to do. Not entirely derive, or at least try to figure out কোথা থেকে এটা আসছে. So PV equals to nRT is called the ideal gas equation. So before people derive this equation, by the way, before I start, are you aware of this equation? Achha, can anyone tell me what is this equation about? No, it is a buchi, but what is this equation for? Huh? Achha, so basically this equation that you see here explains how gases behave, right? But temperature barle, pressure barle, volume barle, ki hobe. So equation I'm asking this question because I want to know, are you convinced with this equation? Do you think this equation works? On ideal gases. Achha, so that means in real life I can't use this equation. No. Then what do I do for real life gases, which are not ideal? No. Achha, so let's say there's a large factory where they're use like a chamber to produce oxygen, and there's a chamber in which there's oxygen, and you want to increase the pressure, decrease the pressure, right? But what's the equation they use? Is there a different equation for every scenario? No, it's this equation, right? But this equation comes with a catch. This is only applicable for what gas? Ideal gas, right? So my point is, a ideal gas equation যেটা তোমরা use করে আসছো, এটা কি real life scenario তে applicable নাকি? So it turns out yes, right? But this ideal gas is based on a particular criteria. What is it? That the gas needs to be ideal. What's an ideal gas? What's ideal about it? So that's what we're gonna see right now, okay? And ওইটা দেখে you might have a change of opinion, okay? যে এটা real life মনে use করা যাবে না. So let me tell you what an ideal gas is. So an ideal gas is a gas that has 11 different assumptions made. Our syllabus has only 5 of them, but there are total 11 assumptions, total, okay? The first assumption that we make for an ideal gas is that the particles in the container are all what? Identical in every manner possible. What does that mean? So they are same shape, same size, same mass, everything is same about them, right? As far from what reality is, because if I go into this room and I apply ideal gas here, that's our ideal gas কাজ করবে না, because does this room only have the same type of atom? No, there are diatomic, there are triatomic molecules, monoatomic. There's helium in the room, right? There's argon. There are random gases out there, water vapor. You get my point? So can I use ideal gas for this room? Most likely no. Why? Because what did the ideal gas assumption state? That this is only possible for what kind of a gas? A gas where all the particles are what? Identical. Okay, so that's the first assumption. Second assumption, so I'll write these down here for it. Second assumption, the particles, right? They collide in an elastic manner. If you remember what elastic means, it means that they do not lose kinetic energy. So the particles collide with the walls of the container, but they do not lose K. So they go back and forth, and they'll continue to go back and forth for eternity. Why? Because they're not losing what? Energy. So there's no loss in kinetic energy. Okay, so that's the second assumption, which also seems absurd. But because real life, when particles collide with stuff, wouldn't they lose energy? So that doesn't really make sense, right? So far, ideal gas seems far from reality, right? Third assumption, these gases only experience the forces of impact. No other force acts on them. So there's no gravity acting on them. There's no electrostatic forces acting on them. The only force they experience is when they collide. So the particles only collide with the walls of the container. That's only when they experience force. Other than that, there's no other force acting on them. Clear? So once more, identical, elastic, but there is no other forces acting on them, right? Then the other assumption, it's a little difficult to understand, that the volume of the ideal gas is very negligible compared to the entire volume of the container. বুঝছো what I meant? So আমার যদি এই রুমের ভিতরে ideal gases থাকে, we have to assume that the volume of the gas is very negligible compared to the volume of the container. Okay, so so let's say this room is a container. So how much gas should be there in this container comparatively? Something like a fistful. That's the amount of gas here, because comparatively very compact of it. Then some students will start having questions like why this assumption, right? I'll explain. There's justifiable reason behind each of them. So we are done with 4 of them. Identical, elastic impact, no other forces acting on them. That no other forces acting on them also implies that there's no energy available, potential energy, right? And the volume of the container is what compared to the volume of the gas. The volume of the gas is negligible compared to the volume of the container, right? So yeah, taking this into account, so there's something about time of impact. When the particles collide with the walls of the container, the time of impact is very negligible. So it's not like they come and collide and stick and then they move off. It's very negligible. So using all of this, we came across what equation? PV equals to nRT, right? And then this is the surprising bit. Listen carefully, okay? We took this equation and tested it out in real life scenario. So we took this equation and tested it in this room, for instance, right? And surprisingly, it works perfectly. So if I use PV equals to nRT for this room right now, right, everything will work as expected. When you temperature বাড়লে দেখবা pressure বাড়তেছে, তুমি number of particles কমাই দিলে pressure কমতেছে, as the equation suggests. which is a problem. You know why it's a problem? Because this equation is based on some very absurd what assumptions, right? তাহলে যদি আমরা ইকুয়েশনটা কাজ করে থাকে, wouldn't that mean the assumptions are right? So what I'm trying to say, because my equation is working right now, and the equation was designed based on the absurd things I told you. Doesn't that mean that the absurd things are the reality? Otherwise, can equation the catch korbe? So now we have to go back again and explain why those things that we mentioned were actually justifiable. So let's start with the first one. What did I say? The first thing, that the molecules happen to have same shape, same volume, same everything. That's not true, right? They're all different shapes and sizes. So how is it justifiable? So it is justifiable because hydrogen, water vapor, some other random element, something else. These molecules, nitrogen, right? These molecules are so small and they're so far apart, right? That from the scale of where things interact, these all appear what to you? Like এখানে কি দেখতে পারছো? So which is what? So I'll just দেখা যায়? আচ্ছা, okay. So I'll shuffle them around. আচ্ছা, so shuffle করে now figure out which one was hydrogen. I think it's anyways, you guys saw it, but the point is that our point of view is so far and the particles are so far apart and so small, they actually genuinely appear what? Yeah, they're same size, same mass, same job pitch. They're so small and so far apart. That's why it's justifiable. You get my point now? So what we're going to do is we're going to justify all of these individually. So the first thing is the same shape, size, and mass is justifiable because we're dealing with what? Very small particles which are very far apart, right? I give the analogy of stars. So when you look at stars, right, they all appear what? Dots. But are they exactly same? No, some stars are like, size of our solar system, right? But they appear as a dot. Our indicator star is which is barely a star. It's like almost a planet, right? Proxima Centauri, let's say. It's also a dot. So they all appear dot Y because, yeah, they're very far apart. And then they're big, but they're very far apart. So eventually the size doesn't really matter to us, right? But once upon a time, people thought stars are pyramids, like, pyramid shape, right? Would that be possible for us to understand from our point of view? No, they still appear what to us? Dots, right? And that confusion still lies with gases, by the way. We still don't know what gas molecules look like. Even though it's not a known fact. It could be a sphere, it could be cylindrical, who knows? From our point of view, we understand that the best shape would be what? A cylinder. Okay, let's go to the next one. Second thing, the particles undergo what impact? Elastic impact, right? How is that justifiable? So shouldn't there be energy loss? But I'm saying there's no energy loss. And the equation eventually proves that there's no energy loss. So how is that possible? Right, that's it. So collectively. So what's actually happening? Let me explain. So imagine you have a molecule here. The collision that we typically know of, right, doesn't really happen in subatomic level. So there's no impact in subatomic level. What actually happens? So you have a charged particle, right, and you have a wall. The wall has charge on it. What does your charge also have? Charge. As the particle starts to get very close to the charged wall, it starts to experience what? Repulsion. And it slows down. There's work done against repulsion, slows down, and stops. And that repulsion then speeds it back up to what speed? Original speed. It's like a ball going up and coming down in projectile. Doesn't it regain its energy all the way back? So that so-called impact is not really an impact. It is actually what? Just change in direction due to repulsion. Is there a possibility of loss in energy there? No, because there's no physical contact there. There's nothing to lose energy to. It's a process of slowing down, turning, and then going back. So therefore, we can assume that the impacts are what? Elastic. So what I meant. But typically, what would happen in a macro scale, not microscopic scale? Things will hit, and you hear sound, right? And because of that, what is lost? Energy is lost. But in subatomic level, if you were an atom, let's say, your universe is a vacuum. Do you understand that? Because you are the thing that makes a vacuum, not a vacuum. So everything is just a vacuum. So when you go very close to a wall, you slow down and then you speed back up again, right? There's nothing to lose energy to. So therefore, you gain back your energy. The only time you might lose energy is if you come in contact with another particle. And that is very rare because the particles are so far apart. It's like once in a million chance that they'll actually collide with each other. Okay? So again, that's justifiable. Third thing, no forces other than Impact forces. So what are the other forces you are looking for? Gravity. Why is gravity not a factor here? It's extremely small, right? 6.67 into 10 to the power minus 11. And the other one is what? Electrostatic. Why is that not a factor? Because the particles are extremely far apart. So that's another justification, right? Our last টা কি বলছিলাম? Yeah, এটা একটু odd. It actually originally ছিল না. Originally, the problem was, look at this. People who came up with this ideal gas equation, they said that container could be a container, right? But then people came up with a refute that if your container is a certain size and your gas is very similar to the container size, it might turn itself into a what? Liquid. Because the spacing is not going to be much. You understand what I'm trying to say? So imagine my container is very small and there's gas inside it. As I start to compress the gas might turn itself into what? Liquid. And it will stop behaving as what? Ideal gas, right? So how can I ensure that my gas behaves exactly like how gases are meant to behave? If you give them enough what to move around, space, how do you ensure that? You make your container extremely large compared to the size of what? The gas out there. So wouldn't that mean your gas molecules have full freedom to move around? So ওইটাকে assert করার জন্য they make this assumption. Okay? So yeah, with all these assumptions, we finally come across this equation. In the next class, I have to detail that. Okay? I'll write it down for you next class.